Hello and welcome to my new video. This time I will speak about Cartesian distributions again. My first video about Cartesian distributions was about using them for background decorations. This time it is about using them for visualizing biological tissues. All copyright skipped to this video and to all other videos from this playlist can be found on GitHub. The link to my GitHub account is available in the comment section of this video. Let's start with a short reminder about the differences of Cartesian and polar distributions. Both times it is about defining the positions of a certain point in space. Cartesian distributions will use the three coordinates of this point, x, y, and z, while polar distributions will use only one coordinate, here the x coordinate, and two subsequent rotations around the two other axes. Here you see a Cartesian distribution for 2 and 3 dimensions. I already showed how to produce such distributions in another video, so here I will talk about this only shortly. Basically, we use three nested loops, distributing elements regularly along each coordinate. We can either directly shift certain objects to the positions calculated, as here, or we can store the positions in an array for somewhat more complicated operations, as outlined below. This regular type of a Cartesian distribution is rather limited in applications. It may be used to model crystal structures, for example. For more general applications, however, we have to introduce some randomness. In this case, I added a random amount and direction of variability to each position with the maximum variation corresponding to the distance between two positions. If we subtract these spheres from a blob, we end up with a sponge-like structure, characteristic example given for real sponges or for the sponge parenchyma from leaves. Another type of tissue leaving large airways is the stellate parenchyma. This can be modeled as well, starting with our randomized Cartesian distribution. We start this model with smaller spheres occupying the same positions as the larger spheres before. Then, for each of these positions, we search our array of positions for positions within a certain distance for this given position. These positions in close vicinity are then connected by cylinders, and the whole structure is combined into a block. This structure here is too complex to really apprehend it by eye. Therefore, I have produced a thin optical section of it. Note, not the perfect stellate parenchyma for sure, but a first good approximation. With this structure, I want to finish my video on 3D Cartesian distributions and cellular structures. Most cellular structures cannot be modeled by this simple approach, since cells often are located close to each other, pressing against each other and deforming each other. It will take some time till I will speak about such interactions, but again, blobs will be the tools of choice to model them.